It's like a what? I am like a DJ. I feel like there's probably already a lot of DJs named like Chemical or something, but for different reasons. I don't know. I don't know. Think of a good one. That's your assignment. You got one? What do you got? Okay. All right. We'll add it to the consideration. All right. Again, sounds like for different reasons, but okay. Let's talk about let's talk about this issue of pressure first, and then we'll look at how we describe the things that we just saw. Oh, this is pretty annoying. Okay. So first of all, we need to know what this idea of pressure is. Does anybody know what the definition of pressure is? What is pressure? Like something? I mean, you know kind of what it is. This is one of those things, again, where we all sort of know what we're talking about, but we really need to define it, like liquid or solid. So for this one, pressure is defined as a force, whoops, not volume, per unit area. So a force applied over an area. And that's what the gas is doing. So that means that pressure units are often going to be dealing with a force and then an area. But because they're so common, they're usually renamed into something else. So the common units of pressure that we're going to talk about are the atmospheres, or atmosphere. That's a really convenient unit of pressure because the atmosphere, all the air, that goes around the Earth, exerts a pressure on the Earth of 1 atmosphere at sea level. So as you go above sea level, high up in the mountains, that pressure gets smaller. But at sea level, which we roughly are at here, the pressure that the atmosphere is exerting is 1 atmosphere. So that's a convenient unit for that. So you'll see that one used. Another one that you'll see is millimeters of mercury, which is a weird unit. Sometimes also more commonly now known as torr. That's a strange pressure unit because it's milliliters, or millimeters. So it sounds like it should be a length. Where that comes from is something called a barometer, which is an instrument that was originally used to measure atmospheric pressure, where the atmosphere would force some mercury to go up a tube, like up an evacuated tube, and how high the mercury would go would determine the pressure. More pressure, higher up in the tube. So that means that it would go that many millimeters up the tube. For conversion here, 1 atmosphere is 760 millimeters of mercury. You don't need to remember any of these numbers. I just want to give you a sense of how big these different units are. All right, another one. So there's some other ones that we won't use as much that I like pascals and some other stuff. So we'll stick with those. There's also the English units, and because in different fields, just depending on what was done historically, that's what you see. It's worth talking about the couple that you'll probably see in the medical field. One being inches of mercury. This is what barometric pressure is usually measured in, like the atmosphere. Like if you look up on the Weather Channel, what's the atmospheric pressure, and it's like 28 or 29 or something. And you can tell kind of what's going on by how much rain is expected or predicted based on the pressure. That's usually in inches of mercury. So same idea, forcing the mercury up the tube, but in inches instead of millimeters. And then the other common English unit is pounds per square inch, or PSI. Can I get this bigger? There you go. So that's how you fill up your tire pressure and things like that, is usually using pounds per square inch. So these are all different measures of the same thing, which is pressure. And pressure is primarily only measured when we talk about gases. Anybody know why we don't talk about pressure with other things usually, like solids and liquids, unless you're talking about geology or something? It's because solids and liquids are not compressible. You can't actually exert pressure on a liquid and make it take up less space the way you can with a gas. So with a gas, pressure is super important because, as we talked about before, is this going to reach? All right. This 100 milliliter beaker always has 100 milliliters of gas in it. But depending on the pressure of that gas, that could be actually more or less amount of gas, more or less moles of gas. If this were under really high pressure, that 100 milliliters would be a lot of gas molecules. If it were under really low pressure, it would be very few gas molecules. So that's why pressure is so important when we talk about gases, and that's what it's measured in. All right, let's look at the... Oops. Let's look at the gas laws. The gas laws are the way that we talk about these relationships that we just saw. And the only important thing that you need to know about them is the relationships. So not the names or the equations or whatever, but what the relationships are. I am going to list the names and things here just so we have them. So the first one we saw in there is called Boyle's law, which is pressure and volume. And just says pressure and volume are inversely proportional, which means when one goes up, the other one goes down. So in the example that we did in there, as we decreased the pressure by sucking the air out of that container, we increased the volume. And that would work in any configuration that you can imagine of those. So any of the four possibilities. Raise one, the other lowers, lower one, the other raises, and then flip them. That works too. We also talked about when we change the volume, like in the breathing, how that affects the pressure. You can feel that in something as simple as like a syringe. If you take a syringe without a needle on it, you put your finger on the end, again, without a needle on it. You stop it up and you push the plunger, you increase the pressure, right? Because you're decreasing the volume. So the gas that's in there that can't get out, the pressure is going up, or the pressure has gone up that way. You can do the opposite as well. You can put your finger on it, pull the plunger out, you increase the volume, which lowers the pressure. Okay, the next one we looked at was called Charles' law, which is temperature and volume. Temperature and volume we would say are directly proportional, which means they change in the same direction. So if you decrease the temperature, as we did by pouring the liquid nitrogen on the balloon, we decrease the volume. We didn't have an example of it, but that works in the opposite way too. You can decrease or increase the volume and change the temperature that way too. And the next one, I think it's not actually in the book. It's sometimes not given its own name. Sometimes it's called Gay-Lussac's law. Sometimes it's just whatever. So we'll just call it pressure and temperature. Pressure and temperature are also directly proportional. So as we increase the temperature by putting the ball, that metal thing, in the hot water, we also increased the pressure. So my idea here, or my hope, is that you don't need to like study these and be able to just recite them from studying them. My hope is that you can think about what we did in the other room and just figure it out from there, because that's easier to remember. So if you think about, okay, which of this thing we did with where we affected temperature and volume, well, we changed the temperature of the balloon and it got smaller. So that tells us the temperature went down and the volume went down, and therefore that's temperature and volume both going down at the same time. So those sorts of things. If you keep connecting this back to the demonstrations, I hope it'll stick in your head all right. All right. Any questions? Yeah. You don't need to know the names. You don't need to know the equations. You just need to know the relationships. All right. Let's move on. Talk about solutions. So that finishes up chapter 5 for us. We're not going to really get into the solids part of that. We did talk about the liquids and the intermolecular forces piece. That was the most important part of that chapter. For liquid, or for solutions, I actually want to check Blackboard because I don't have my bag here. Of course, I'm expired. Sure, we're doing this right. Okay. So we talked about solubility a little bit. We talked about how only things with similar types of forces can dissolve in each other. So like ions can dissolve in water, but they can't dissolve in nonpolar compounds. And we're going to use that now. We're going to use those ideas to talk about a few different things. So first of all, let's look at a couple definitions. Electrolyte. Does anybody know what an electrolyte is? It is not exactly Gatorade. Well, Gatorade contains electrolytes. Have you ever seen that movie? They're what plants crave. No, nobody. Yeah. Yes. So Gatorade has electrolyte, but what is an electrolyte? It's pretty much magic. Yeah. An electrolyte is any compound that produces ions in solution. So if we look at something like sodium chloride, if you dissolve it in water, and we're going to use a little bit different notation here just because it's not quite a chemical reaction. If you dissolve it in water, what you have is aqueous sodium chloride. But as we talked about last week, what that actually is now separate aqueous ions of sodium and chloride. Ions that have been separated and surrounded by water and are no longer together the way that they would be in the compound. They're no longer, the positive and negative ions are no longer close together. They're separated throughout the solution. And so that's an electrolyte because sodium chloride produces ions. But ionic compounds like that are not the only types of electrolytes. Some acids like HCl, which is a gas in its pure form, hydrogen chloride, can also mix with water. And it actually transfers its hydrogen to the water and makes something called hydronium, which we'll talk more about this when we get into the acid and base chapter next. But it makes this ion called hydronium, which is H3O plus and Cl minus. So it's not splitting up in the same way that an ionic compound does, but it's still forming ions in solution, and so that's still an electrolyte. The reason it's called an electrolyte, the reason it has that electro word in it, is because when you have ions in water, that solution can now carry a current, can now transmit electricity. Pure deionized water cannot conduct electricity. It has to have some ions dissolved in it to conduct electricity. The reason tap water or like puddles on the ground conduct electricity is because they have salt and other stuff in them just because they're not pure water. But pure water is not an electrolyte. All right, so if water is an electrolyte, or if water is not an electrolyte, we put these compounds in, and then those compounds are then called electrolytes. We can also separate those into two categories: strong electrolytes and weak electrolytes. In a strong electrolyte, well, no, let's change that. We'd say a strong electrolyte completely dissociates into ions in solution. So it completely splits apart and forms ions. Whereas a weak electrolyte only partially dissociates. So there's still going to be whole compounds laying around, but there's going to be some ions. And then a non-electrolyte makes no ions. So a good example of that is sugar, sucrose. If you dissolve sugar in water, it dissolves, but it doesn't split into ions. It's still whole molecules. The molecules are just separate and surrounded by water molecules now. It hasn't formed any ions. So in order to be an electrolyte, something has to form ions, which means it has to be either an ionic compound or an acid. All right, so then why does Gatorade advertise its electrolytes? Yeah. What why are electrolytes important for drinking stuff? Or is it just marketing? Kind of. What about it? What's necessary? Yeah. Well, yeah, so what comes out in your sweat? Somebody said it. Yeah, ions. So particularly sodium chloride, because your sweat is salty, right? Like if you taste it, it's full of salt. Yeah. So a lot of ions are coming out with the water when you sweat. And so if you're only drinking water, there is a risk that at some point you will have not enough ions in your body to do all the stuff that ions need to do. Particularly, um, they run your nerves. And I don't know, I've never taken physiology, so I'm just going to leave it at that. They run your nerves. You can all take physiology and tell me what actually happens. But it has something to do with your nerves. So for most people, it's not an issue. So the Gatorade thing really is mostly marketing. But if you are exercising intensely for a very long period of time, like in a marathon or something like that, you will need to replenish your electrolytes, your sodium chloride, and other ions that you've lost through sweating. Um, yeah. And if you don't, if you only drink water and you don't get that sodium, it messes with your nerves and you can have seizures and other stuff and eventually die. Yeah. But not just from like you don't need Gatorade because you're playing a quick game of something. I don't know. What's the sport? Frisbee. Yeah. You're going outside and playing some frisbee. You probably don't need Gatorade to replenish your electrolytes. You just need some water. All right. So that's electrolytes. Let's talk about. Yeah, you have. That's what advertising is. That's like the whole definition of advertising. Just lying to people to get them to buy stuff. Um, what's another good one? Sorry, this is a little off topic, but it just reminded me. Have you ever tried to buy pet food recently? Does anybody have pets? I don't know if you have some pets. So the big thing with pet food is they advertise grain free. You can get like grain free food. No, it is grain free, but there's no reason that any dogs need to avoid grain. Like it's just marketing. Because most dogs, if they have allergies, they're allergic to meat and protein, like different proteins. So it's kind of well, I mean, look, if your vet prescribes a particular diet or something, that's one thing. But in general, there's this big thing, and then there's not actually a reason that dogs need these special foods. So, I mean, if they like it, then whatever. But yeah. All right. So sorry, that was off topic. Um, okay, let's talk about some definitions of solutions, and then we can talk about concentration. So, a solution is really just a another word for a homogeneous mixture, a mixture of two things where um, they have so completely mixed that you can't tell any phases apart. And in general, the word solution is used to mean that that is true all the way down to the molecular level, so that the compound level, so that if you have like sugar in water, let's say, you have pretty much individual sugar molecules surrounded by water. And so that means you could never actually see the different domains, even with powerful microscopes. There are two parts of a solution. The solute and the solvent. Now, these words actually have a pretty simple definition. The solute is just the thing that there's less of. And the solvent is the thing that there's more of. with the exception that water is almost always the solvent, even when there is less of it. So I'm defining that very generally because solutions can be a lot of different things. Air, for instance, is a solution. It is mostly nitrogen, so the solvent is nitrogen, and all the other stuff is dissolved in the nitrogen. The oxygen, the carbon dioxide, the water vapor, and all the other little bits of trace gases. The solutions we're mostly used to are the things where we like dissolve a solid in water, like sodium chloride dissolved in water, where sodium chloride is the solute, water is the solvent. But the solute can also be a liquid. You could dissolve things like ethanol in water. You can dissolve gases in water, like we just saw. HCl, hydrogen chloride dissolved in water makes hydrochloric acid. And then you can dissolve whatever and whatever else. You can actually dissolve solids in each other too. Something like brass is actually a solution of, I believe, copper and silver. I think that's true. That might not be true. Let's look that up. Might be something else in there. Copper and zinc, sorry. So we usually call those alloys when they're solids, but it's really a type of solution also. Forgetting I'm in a different program right now. Whoa. All right, I made it disappear. Let's try that again. Okay, that's easy. Whoops, I don't think that's right. Yeah. Sorry, everything has to be more complicated. There we go. So to know how much solute is in a given amount of solution, we need to know something called the concentration. So if you're measuring out a pure solid like sodium chloride and you want, you did your equation and you did your moles and whatever, and you figured out you needed 26.3 grams of sodium chloride. That's pretty simple. You get your scoop, you get your sodium chloride, you weigh it out on the balance, you put it in, you're done. But if you have a sodium chloride solution, if you have some sodium chloride that's already been dissolved in water, how do you know exactly how much sodium chloride is actually being added to whatever you're doing? So to know that, we need something called the concentration, which tells us how much solute is in a given amount of solution. So how much of the stuff that's dissolved is dissolved in a given amount. And there's no single measure of concentrations. There's lots of different ones. We're going to focus on a couple of the most important and most widely used measures of concentration. So the first one we're going to look at is probably the simplest, and it's called mass percent, or percent by mass. And it's sometimes written as percent m/m. And this is, as it sounds, simply a percent of how much mass is solute compared to the whole solution. So it looks like this. That's a percent sign, yeah. So the percent by mass is calculated by taking the mass of the solute divided by the mass of the solution times 100%. Now that's not some fancy kind of equation, that's just a percent. So It's simply dividing two things, like taking the percent of it. So if we have a 25% solution of sodium chloride, that means that by mass, when we weigh it out, that solution is 25% sodium chloride. Whatever that is, you calculate your percents and you've got it. A related one that is just as simple is the volume percent. Or percent by volume. Which again is also just a simple percentage of how much is solute and how much is solvent. Or sorry, how much is the solution. The only tricky thing or potentially tricky thing about these, and if we have time, we'll do a couple examples, is that if you look in the denominator, make sure that you're using the entire solution as your denominator, because that's how percents work, right? You have the whole on the bottom, and the thing on the top is what you want the percent of. So volume percent is more useful when both things are liquids. So let's say you want to make like a solution of ethanol and water. Those things are both easier to measure out by volume than by mass. So you could measure out, 40 milliliters of ethanol and then put it in 100 milliliters of solution, and you'd have a 40% solution. That's how things like alcoholic drinks are measured. If you look at the alcohol by percent by volume, ABV that's on alcoholic drinks, that's a percent by volume. So how much of this volume is ethanol? And then the third type of percent is the one that's a little bit weird. It's kind of a hybrid of these. So what ends up happening is, okay, so usually it's easier to weigh out your solute if it's a solid. And then it's easier to measure your solution by volume, because once it's dissolved, it's like a liquid and you can get a volume. So this way you can do both at the same, you can use both of those measurements together. And that's called percent mass by volume, or mass volume percent. And that is specifically the grams of solute divided by the milliliters of solution times 100% again. So again, it's a percentage, but it's grams divided by volume. So there's an example in the book here. Let's take a look at it. Room here. Calculate the mass volume percent of 0.300 liters of solution containing 15 grams of glucose. So you want to put 15 grams of glucose in 0.3 liters of solution. Use the equation from up above. Percent mass by volume is the grams of solute divided by the milliliters of solution times 100%. So in this case, that's going to be 15 grams of glucose. And then our solution here is given in liters, so 0.3 liters is how many milliliters? 0.3 liters. That conversion real quick. We need milliliters of solution in the denominator. So what's 0.3 liters in milliliters? 300? Yeah. All right, so 15 divided by 300 is 0.05. And then we want to make that into a percent. So that is 5%. So we would say that this solution is 5% mass by volume glucose. And that little m divided by v thing is important because whether it's m divided by v, v divided by v, or m divided by m, those numbers are going to be a little bit different. So whenever you see a percent as a concentration, you need to know which type of percent it is. And especially when you talk about things like medication, next time you have to take some sort of a liquid medication or a solution, or if you have like a bag of fluids or something like that, you can see on there different types of solutes will be measured in different units, and the percentages will be given in various ways depending on how it's being measured. All right, so those are the percentage-based measurements. Any questions about that? I'll do percents. It takes a little practice, but I'm sure you'll get it. The last concentration measurement that we're going to talk about is the most important to us in chemistry and is very important in things like intravenous fluids, and that is something called molarity. I guess we'll give that a number 4. This is another measure of concentration. And the molarity, which is a capital M, is defined as the moles of solute divided by the liters of solution. And the reason that this one's so important is because of that moles factor in the numerator in the top of that fraction. If we're doing chemical reactions, remember that everything has to balance by moles. That's how we calculate all our stuff with our chemical reaction. So if we're using solutions, it makes a lot more sense to use your solutions in a way that's already measured in moles to save you a step. So that's why we use it. In medicine, it's important because remember that moles is a count. It's a way of counting particles. And so if you want to count the particles instead of knowing the mass of the particles, then molarity makes a lot more sense. And one way that that comes in is osmosis, which we probably won't get to tonight, but we'll talk about next week. So let's practice calculating molarity and doing some other types of calculations with it. So the first thing we can calculate is just straight up calculating the molarity by given the amounts of solute. So we can say calculate the molarity of a 2-liter solution containing 5 moles of sodium hydroxide. 2-liter solution containing 5 moles of sodium hydroxide. That, we just need to plug that into the equation. So the molarity is the moles of solute, which in this case is 5 moles of sodium hydroxide, divided by the volume of the solution in liters. Mm-hmm. 5 divided by 2 is 2.5. So we would say that this solution is 2.5 molar sodium hydroxide. And you may not have noticed it, but you've seen this measurement a lot on the stuff we've been using in labs. Most of our solutions have concentrations measured in molarity. And so there'll be the 6 molar HCl or the 0.1 molar AgNO3, which we used last week, things like that. So that's calculating molarity. One thing that you may need to do, though, is actually make the solutions in the first place. And if you're making the solution, you can't really just have 5 moles of sodium hydroxide. You're usually going to be measuring it based on a mass. So we have to go back to a couple chapters ago, converting between mass and moles. Let's try another one that is a similar question, but the amounts are going to be given a little bit differently. So once again, we want to calculate the molarity if 5 grams of glucose are dissolved in 100 milliliters of solution. So in this case, it's really the same question as before, just with a couple of unit conversions. So we're given grams and we're given milliliters. But in order to get a molarity, we need moles and liters. So just as in the previous example, if we want to calculate molarity, we need moles for the top and liters for the bottom. So our grams have to get converted to moles, and our milliliters have to get converted to liters. So to go from grams to moles, we need the molar mass. We don't have that here, so we would have to calculate it. We don't even have a formula, so let me just give you the molar mass. The molar mass of glucose is 180 grams per mole. All right, so now that we have that, we can do our conversion from grams to moles, just like we did before a few chapters ago. So 5 grams of glucose. And we want to go from grams to moles of glucose. So that's 180 grams in 1 mole. All right, 0.0278 moles of glucose. So that's one conversion done. Our next one is to go from milliliters to liters. 100 milliliters. We want to go milliliters to liters. There are 1,000 milliliters in a liter. So that gives us 0.1 liters. So the key to these types of questions is you always need your solute in moles and your solution in liters. Now that we have those two, we can solve for the molarity. So we're going to put our moles on top, liters on the bottom. 0.0278 moles of our solute glucose divided by 0.1 liter of solution gives us 0.278 molar as the concentration. So we converted grams to moles, milliliters to liters, and then divide moles by liters to get molarity. All right, the last thing we're going to do is figure out how much of something you might need to get a certain number of moles. Okay. So sometimes we're given a molarity and we want to know how much of a particular solution do we need to give a certain number of moles. So how much of a 0.750 molar H2SO4, which is sulfuric acid, would contain 0.120 moles of sulfuric acid. So we want to know how much of the solution would contain 0.120 moles of sulfuric acid. There's a couple ways to do this. You can do it as a proportion because you know that 0.75 molar is 7.75 moles per liter. But I think we should stick with our same technique that we've always done all these conversion type problems and just use that molarity as a conversion factor. So when we see that molarity, 0.750 molar, we can write that a couple different ways. So we need to know that that means 0.750 moles per liter, or 0.750 moles of sulfuric acid per liter of solution. That's what molarity means. So when you see that 0.750 molar, that's what that actually means. All right, so now that we have that, we see how it kind of looks like a conversion factor with moles on one side and liters on the other side. The rest of the problem is just like the conversion problems we've done in the past. We'd start with that 0.120 moles of H2SO4. That's how much we need. And we want to convert those moles to liters because the question is asking how much of the solution, how many liters of the solution. These numbers come from the molarity. So in this case, the moles cancel, and we're left with liters, and that's what we want. So we convert from moles to liters using the molarity as a conversion factor. So just like with any of these other types of problems, it's just going to take practice. So make sure you're working through the practice problems in the book and online if you prefer that. Next week, we'll talk about dilutions and solution properties like osmotic pressure, and then move into acids and bases. So I'll see you on Lab on Wednesday. Lab on Wednesday is about intermolecular forces, extracting fats from potato chips with different solvents. So be ready for that. Yeah, let me know if you have any questions.